Okay, thanks everybody for joining us on the Learning Lab 21. So this is going to be the last Learning Lab of the year, and after going to stop for the holidays. So I'm going to start sharing my screen. So that's the Learning Lab that we're going to be presenting today. It's actually going to be presented by Brian Russell, and it's about polynomial regression using Python. So just a small introduction, what is the Cruz Data Science Initiative? We are a group at the University of Calgary that is connected with Cruz. We are a subgroup of Cruz, in which we do data science projects that are related to geoscience, the energy sector, and environmental. As well, we do programming training in Python, R, and Matlab that can go from introductory training, like how to use Python, as to applications doing machine learning and how to create apps using libraries such as Shiny in R or Django in Python. And we also provided those learning labs. Those are free webinars that happen bi-weekly. And you can access all the old versions or all the older presentations in our YouTube channel, or you can visit us at the www.cruz.org and see all our previous presentations there. So the hosts are me, I'm Marcelo Guarido. I'm a data scientist with PhD in geophysics and a background in physics. And today I'm the head of the Cruz Data Science Initiative. Daniel Tread, would like to present yourself?
Yeah, hello everybody. I'm a professor at the University of Calgary and working quite actively these days in machine learning as well.
Now, David Emery, would you like to present yourself?
I'm David Emery. I am assisting Marcelo and Daniel with the Data Science Initiative, and actually right now in my retirement doing a PhD with Daniel in machine learning.
Now, our also co-host and presenter today, Brian Russell.
Hi everyone, Brian Russell, and I'm Vice President of Geosoftware and also a Cruz associate. I'm on the Cruz staff, so it's great to be here today, and well, hopefully you'll learn something.
For sure we will. And I think that's it for my part. Now we're gonna pass to the presenter. You can share your screen.
So I'll share my screen now.
Yeah.
Okay. So I'll just say the whole screen because I'm going to be showing first a PowerPoint, and then after that, I'm going to get into showing the actual code using Spider.
Oh, cool.
Okay, so run the code. Okay, well, thanks everyone. So this is, I think I got the number right. Is that right? 22, Learning Lab 22?
I think that's the 21, but that's
oh, is it 21? Oh, okay. I'll change that. I added one.
Okay.
Okay, so basically, and of course, we've just had this, the host. By the way, Marcelo, there's 2 L's in my name, but that's okay. It was close enough. So I'll give you a little introduction. Then I'm going to discuss polynomial regression, the primal and dual solutions, have some conclusions. Then I'll do a little demo with my code. And by the way, the code, if you want to link up with the code right now, it's in the chat. We put links to the actual GitHub code if you want to download it, if you've got a compiler running, and then a Q&A. Okay, so let's start with an introduction to machine learning. In machine learning, the input data set generally consists of n measurements, each consisting of m features, or in geophysical terminology, what we call attributes. Mathematically, you can represent this as n m-dimensional vectors. So the two fundamental problems in machine learning, actually there's more than that, but the two most important ones are regression and classification. In regression, we try to predict one of the features using the other m-1 features. In the linear form of regression, we find the m-1 weights, then when multiplied by these features in sum, predict the feature of interest. And there's often or usually a bias weight, which usually means there's m weights in total. More advanced forms of regression involve nonlinear functions applied either before or after the calculation of the weights. And, that depends on the type of algorithm you're using. Now, in classification, we divide the endpoints into K classes and try to find either linear or nonlinear boundaries between the classes. But in my talk today, I'm going to focus just on the regression problem. So basically, regression problems can be broken into two categories, linear and nonlinear. There's only one linear approach, and that's where we're going to start today. But there's a variety of nonlinear regression methods, such as polynomial regression, radial basis functions, generalized regression, neural networks, and so on. And radial basis function approach is often called kernel regression. Linear regression is also a subset of polynomial regression. It's actually the simplest polynomial regression approach and uses a first order polynomial. So in the lab today, I'm going to discuss three types of polynomial regression approaches: linear, quadratic, and cubic. And I'm going to apply them first to a simple three-point problem. And then after you're sick and tired of the 3-point problem, we're going to do a more complex 10-point noisy sine wave, as I call it. And I'm going to start with the primal solution, which in fact, it may be a lot of you are familiar with it, and you don't call it the primal solution, you just call it the solution. But then I'm going to discuss the dual solution, which is not as well known. The advantage of the dual solution is it will lead directly to kernel regression, which I'm going to discuss in the next lecture. Initially, when I proposed this to Marcelo, I said I'd do it all in one lecture. I'd do the polynomial part and then directly go to kernel regression. But what I discovered is there's just too much to cover in one hour lecture. So I'm going to break it into two, where today I'm going to focus on polynomial regression, and then I'm going to sow the seeds for looking at kernel regression in the next lab, which will be in the new year. And as I said, it's a fairly simple problem. So to really do it justice, you have to use a lot of features. And in fact, in Hampson-Russell eMERGE program, we use multiple features. So you call it multivariate regression. But to make life simpler, I'm going to let m equals 2. So we've just got two data sets, two vectors, x and y. So each vector has n samples in it. Okay, so in polynomial regression, what we want to do is find a set of weights. So we'll transform x into an estimate of y, which I'll write as y with a hat. So y hat is equal to w0 plus w1x plus w2x squared plus ... plus wp x to the p, where p is the pth order polynomial fit. And so this is actually going to lead us to a lot of very interesting concepts like ridge regression, dual representations, and kernel regression, which, as I said, will be covered in a second lecture. Now, here's even simpler. I'm going to give you the simplest non-trivial example I can think of. And this is an example I came up with about 20 years ago when I was first writing the eMERGE course, because I was having trouble explaining how the nonlinear regression methods like RBFN and GRNN worked. And so I came up with this very, very simple problem. And at first I was just using it for the nonlinear approaches. Then I realized it's good for every example. So if you plot it, it looks like this. It's just 3 points, but it's complex enough that it contains all the elements of regression. It'll teach you regression very well. So it raises several interesting questions. Is there a single straight line that will give a perfect fit to these points? And I think you all see that the answer is obviously no. If the 3 points were collinear, the answer would be yes. But the fact that don't line up in a straight line, you can't find a single line to fit them. Is there a polynomial fit that will give an exact fit to these points? And the answer is yes. And third is, will we get a better fit by increasing the order of the polynomial to large values? And the answer depends on how you define better. It might look better, but I'll show you there's a reason why it's not better. It overtrains if you use too many polynomial terms. So let's expand the previous equation in our example. So we've got 3 points, and I'm going to expand it to, so each point is going to be W0 plus W1x1 plus W2x squared, and so on. And we go out to an order P. Now, notice we have 3 equations, but P plus 1 terms. So if P plus 1 is less than n, this is called the underdetermined case. If P plus 1 is equal to n, this is called the even determined case. And if P plus 1 is greater than n, this is called the overdetermined case. So let's illustrate this using our 3-point example, which leads to linear, quadratic, and cubic curve fitting. So let's let P equals 1, which is the simplest possible problem. This is just a linear fit. We've got 3 equations now with only 2 unknowns, so it's underdetermined. So y1 is W0 plus W1x1, y2 is W0 plus W1x2, and y3 is W0 plus W1x3. Now, of course, we can write this in a matrix form. We can write it as y equals x times the weight vector, where x now has a column of 1s that coincide with the W0 terms, and 1, 2, 3 in the second column. So x, so the first column is all 1s, the second column is 1, 2, 3, the x values. And W is simply a 2-valued vector, W0, W1. I should point out that this is where it can sometimes get confusing, because the statisticians and the electrical engineers use different representations. Sometimes X is written as a horizontal matrix. And so sometimes they use X transpose as this matrix, but I'm going to use this terminology, so where it's vertical vectors. So ideally, we'd like to solve for the weights by inverting X. So we'd like to say W is equal to X to the minus 1 times Y. The problem is you can only invert X if it's square. That is, N is equal to P plus 1. You have to resort to a least squared solution. And the least squares solution without any kind of pre-widening or ridge regression is like this. It's X transpose X to the minus 1, or the inversion of X transpose X times X transpose Y, which I can write as A to the minus 1 times C, where A is the covariance or autocorrelation matrix, and C is the cross correlation vector. So our solution mathematically looks like this. And if you're not familiar, if you're familiar with matrix algebra, you'll see it's just I've done the thing explicitly, and we end up with weights of 1 and 1/2. So when I draw the regression line, the y hat is equal to 1 plus x over 2. Very simple regression line. So that's one way of writing the solution. There is another way. Before I get to that, note that you can also say, if you've got a set of unknown points x0, for every x0 point, you can simply write the solution as 1x0 times W0 W1. So that's the way to implement the actual solution. So for example, y of 2.5 is 2.25, as you can see there. And so this is the complete regression line. Those of you who are familiar with different programming languages, will see that in my previous slide, I've actually plotted it using Python. This one is from Matlab, where I actually do most of my coding. All right, so an alternate way to arrange the solution is like this, where it's the same solution, but now I'm grouping the terms differently. I'm gonna group the terms X transpose X minus 1, X transpose, into one group called X dagger, which is the generalized inverse, or sometimes called the Moore-Penrose inverse. And the generalized inverse will give us the same solution as we got in the previous approach, but the solution is kind of has a different interpretation. Now you can see it's the weighted sum of the 3 terms. And it's actually, I think this is a better way to see the solution, because you can see that it's 4/3 times 1 plus 1/3 times 3 minus 2/3 times 2, which gives me 4/3 plus 1 minus 4/3, which is 1. And likewise, the other one, minus 1/2, 0, 1/2, gives me 1/2. So we get exactly the same solution. It's just we've grouped the terms differently. All right, so let's take a little break now and look at, I will look at the Python code later, but I want to, it's hard to read Python code on the screen. So I blew it up here and just a few comments. In Python, first import the necessary library. So I'm going to import matplotlib.pyplot as plot, plt, numpy, you always need numpy, np. And I'm going to import, because I'm going to be doing inversion, I'm going to, from the linear algebra in NumPy, I'm going to import inv, so I can just use inv as my inverse operator. And then I'll create the input, n equals 3, and x is equal to np.array 1, 2, 3, y is np array 1, 3, 2. And this is a gotcha in Python. I discovered the hard way. If you code it as np as array, which strange Python things, needs 2 square brackets, it doesn't always do what you think it is. If you want an actual vector, you've got to code it up as an array. So Python is a very rich language with many types of arrays. Unlike Matlab, which just an array means a matrix in Matlab. Then you compute the regression coefficients. So I'm going to say 1 is NP ones. Ones just gives me 3 ones. Then I'll do a column stack. And by the way, you can also use np.concatenate, but I find column stack works better. Also, the x.t and y.t is a simple way to transpose a matrix or vector. But again, in MATLAB, you can always use the np.transpose operation to do the transpose. But I like that .t. So C is a covariance matrix. It's x.t times x, using matmul, a matrix multiplication. C inversion is the inverse of C times transpose of x. And then the weights are simply multiply C inversion times y transpose. Okay. Then we compute the regression line. The simplest way to do that is to use what's called linspace. And linspace is a shameless ripoff, as I say, of the MATLAB command. But that's nice for MATLAB users. There's a lot of things they've coded up in Python that come directly from MATLAB. So I'd say start at 0, go to 4, and divide it into 100 points. So start n num equals m, and then just say y naught is equal to w naught plus w1 times x naught. And you finally plot the data. So plot figure 1, use scatter plot for the 3 points, a full plot for x naught and y naught, put the title on, the labels, and so on. And you can also, actually, there's 2 ways to do the scatter plot. You could also use a MATLAB type operation where you do plot and you, in quotes, you put K0, which just means black, put black zeros in. But so either way, it'll work. Okay, so now let's move to p equals 2. Then we've got 3 equations with 3 unknowns. So now you actually have a square matrix. So you've got 1, 1, 1, 1, 2, 3, and then 1, 4, 6, which is the, oh, that's a typo, isn't it? That should be 9. That should be 9 there. I don't know why I put 6. All right, let's fix that. And okay, so getting back to this. And now, since it's a square, it can be inverted directly, and you get something like this. So the quadratic fit is perfect. It fits the point. So we've got -4, 6.5, minus 1.5. So the y hat estimate is -4 plus 6.5x minus 1.5 x squared, which looks really nice, except you can see how rapidly the curve drops at both the left-hand and right-hand side, which might not be the best fit if we observe more points. Just because you get a really good fit to your points doesn't mean it's a better fit, because when we start observing more points, you might find they don't go negative. They're all positive, in which case the linear fit would probably be better. Okay, so how did I do that in Python? I did a X as a column stack of 1. I created the square X square, this np.power X of X raised to the power of 2. Then I stacked 1 X and X squared. And I did the inversion. I multiplied it. I didn't need to do a least squares inversion this time. Then I created a regression line. So now I have to create what I call X naught squared. So now Y naught is W naught plus W1 X naught plus W times X naught squared. By the way, I said earlier, if you don't use the right array functions, you get into trouble. If you use NP array, you can actually do a Matlab type thing where you extract those weights as just W of 0, W1. If you don't do that, if you use the other type of array, you have to do some kind of strange thing where you identify the values and convert them. So you can get around it, but this is by far the easiest thing to do because this is the way you would do it in MATLAB. Okay, so let's go to p equals 3. This leads to the following set of 3 equations with 4 unknowns. So now we've got, okay, now I think I have my numbers right. We've got a 4th column, which is the cube. So 1, 8, and 27. Now we've got 4 weights, W0, W1, W2, and W3. And we get a set of, we do the inversion, get a set of values that look reasonable. And guess what? It's screwed up. It doesn't look good at all. So what went wrong? Anybody, I don't know, can anybody, Daniel or anybody that can speak? What do you think went wrong? Well, let me tell you what went wrong. The problem is in the overdetermined case, the inversion is unstable. The reason for that, the determinant is equal to 0, the determinant of, so you can't invert that matrix. So to solve the problem, we add a small value to the main diagonal of the matrix before inversion, which is called pre-whitening in geophysics and ridge regression in statistics. So it looks like this. You basically say X transpose X plus lambda times I, where I is the identity matrix. And by doing that, you actually solve the problem. And it can be a very, very small number. I use 10 to the minus 6. I get the coefficients that look like that. And now I get a perfect fit. So notice that the curve fits the points well and looks reasonable. But again, I say, is it reasonable? Well, let's expand the plot. And look at what happens. Because it's a cubic regression, we have a cubic fit will cross the x-axis 3 times. So now you get this big jump up, which doesn't look realistic. There's nothing in that data that suggests that that curve should take a big jump up like that. That's strictly the fact you're fitting a 4-point cubic regression to 3 points. So in other words, unlike the quadratic that intersects at 2 points and a linear fit that only intersects at 1 point. Okay, so this is called overfitting. It means we've used too many parameters to do the fitting. In this case, 4 parameters for 3 points. But just to make things finalize, this is how we actually compute the cubic regression coefficients. And you can see now I've got an extra x cube in there and so on. I think you can see that. So now at the end, y naught is equal to w naught plus w1 x naught plus w2 x naught squared plus w3 x naught cubed. And so I think you can see now, it gets a bit tedious, but if you want to do an nth or a pth order polynomial, all you got to do is keep adding these terms each time. But for the 3-point problem, it's going to overfit quite a bit. So let's go back and apply ridge regression to our earlier problem where I didn't apply ridge regression. So if I use 10 to the minus 1.1, it gives a very poor fit. It's that red dashed line and coefficients aren't correct. But if I use 10 to the minus 6, I get pretty much the exact answer, 1 and 0.5. So my point is here, it never hurts to apply ridge regression. And in fact, we know that in geophysics. Even if we don't suspect we have an unstable or underdetermined problem, we always apply a little bit of pre-whitening. So, okay, so far I've been talking about regression as a single solution. This actually has a name. It's called the primal solution, x transpose x plus lambda. And remember, now I'm being very careful. I'm saying the dimension of that matrix, the whitening matrix, is p plus 1 times p plus 1. Okay. Now it's a little complex, but I finally got the clue on how to do this from a paper or a book I'll talk about at the end. But if you manipulate the ridge regression equation, you can derive an equivalent solution called the dual solution. And the dual solution looks like this. W is equal to x transpose. Now, instead of the inner product, x transpose x, you've got the outer product, x transpose. Now, the identity matrix, instead of being p plus 1 by p plus 1, it's n by n, because when you multiply x times x transpose, you get the number of rows rather than number of columns. Okay, and so notice this tells us that those two forms are equivalent. X transpose t plus lambda I minus 1, or x transpose x plus lambda I p plus 1 minus 1 xt. And as I said before, the only time I'd seen this, Daniel's pointed out he's seen this in several different papers, but the only time I had ever seen this was in Tarantola's book on inversion. So that is, the weights can be computed using either an inverse containing the n by n matrix x transpose, where n is the number of points, or the p plus 1 times p plus 1 matrix x transpose x, where p is the order of the polynomial fit. So let's go back to the linear least squares problem and see its dual form. So now, instead of what we saw earlier, which was a 2 by 2 matrix, now we have a matrix. When you multiply x times x transpose, you have a 3 by 3 matrix, which now, and you can see why it's called a dual, because this now converts what was a simple problem before into, or an underdetermined problem before, into an overdetermined problem. Or did I get that right? Overdetermined. Anyway, you see what I'm saying. So if we take the determinant of x transpose, you get 0. Now we can, for the other one, it was hard to prove, the 4 by 4, but for this one, you can see if you go through the steps of figuring out the determinant, sure enough, it's 2 minus 6 plus 4, which is 0. So it's not invertible. So we have to add a little bit of pre-whitening like this. And the key is to find the optimum value of lambda, enough to reduce the instability, but not so much that the pre-whitening factor dominates the solution. So as lambda approaches 0, the inverse actually approaches something that looks like this, 1 over 3 lambda times that matrix you see there. But it would be incorrect to think that inversion ever reaches this symmetric matrix shown in the limit, since the values there have been rounded off. So for example, if I use lambda of 10 to the minus 1, I get something that looks like this. That's quite a long way from that matrix. It's 10 over 3 times 0.9. So you've got 0.97 and so on, 0.89. If you use 10 to the minus 6, you have to take the solution out to a lot of significant digits before you see. So it's 0.50000061 and 0.49. So it's very close to 0.5 and 0.5, but it's still asymmetric. So that little bit of asymmetry makes all the difference. So the new weights, put them in, you're going to get the right answer, but you're going to get the right answer because you're not quite using you're using a little bit of pre-whitening. So as I showed you before, the actual solution is going to be the same as before. 4/3, 1/3, minus 2/3, and minus 1/2, 0, 1/2 times the 1, 3, 2, which gives you the weights of 1 and 1/2. Okay, so let's have a look at the Python implementation of the dual method, where the code can be used for all 3 of our regression problems. And I'm using GI for generalized inverse. So C now is now the matrix times its transpose. Actually, I didn't use a mat mul here, matrix multiplication. I actually multiplied them together. Now the identity matrix is of n by n. There's the inversion, and there's the final, what I call the generalized inverse. And there's the final weights, the generalized inverse times the y transpose. And as I'm going to show you in the demo, this gives exactly the same weights as the primal method. All right, so even though that 3-point problem gave us insight into all of the regression methods we've discussed today, I do admit it's actually a very boring problem. So here's a more interesting problem. It's a 10-point noisy sine wave. Actually, this problem was suggested by Bishop, and I'll give you the reference to Bishop's book. It's one of the classics in machine learning. And what I did was I generated a single period of a sine wave, and I corrupted it with Gaussian random noise and shifted it by adding a +1, okay? So here are the actual values, the 10 points for the X values, and there's the actual Y values. Okay, so here's the linear fit to the noisy sine wave, where the weights are computed by both the primal and dual solution and give the same answer. So it's 1.03 minus 0.16y. So it's a negative slope. And it's found the trend of the sine wave, but which has a negative dip, but it hasn't found the shape correctly. So let's do the quadratic and cubic polynomials. So here's the quadratic fit. And you can see the weights are 1.33, 0.09. So the second weight is very small. So actually the second and third weights are very small. So it's dominated by the linear trend here. So this is better than the linear fit, but we don't, and if we didn't know that the underlying shape was a sinusoid, we could be looking at a noise corrupted parabola. So this is actually a pretty gentle way of fitting a set of points like this. It's giving a better fit than we got. And by the way, I should have gone in and calculated the root mean squared error, but I never got around to that. So that would show us that mathematically it's a better fit. Okay, now here's the cubic fit. And you can see now you get a pretty good fit. The only problem with this, again, is you're probably overfitting. If you were to think that this is really a sampled sine wave, it's probably going to swing back up and swing back down. So, but the fit will go off to, on the left-hand side, we'll go to very large negative values, and on the right-hand side, go to very large positive values, which is probably not going to fit very well outside of this range. The other thing is if I gave it 2 periods of the sine wave, it wouldn't fit very well. So polynomial fits in general are not great. You're never, unless you have a really nice underlying polynomial, you're never going to get a perfect fit. Okay, so in this talk, what I've done is I've discussed polynomial curve fitting using both a simple 3-point problem and a more complex 10-point noise corrupted sinusoid. We found that for n points on a polynomial order of p, if n equals p plus 1, we get an exact fit to the points. If it's greater than p plus 1, the underdetermined case, we underfit the problem. If it's less than p plus 1, the overdetermined case, we overfit the points. So the primal regression solution involves inverting a p plus 1 times p plus 1 dimension matrix and multiplying the transpose of our data matrix times the data matrix, which is found by that. The dual regression involves inverting an n by n dimensional matrix found by multiplying our data matrix times its transpose. So it would appear for the undetermined case, it would be preferable to use the primal solution as it requires the inverse of a smaller matrix. However, what I'm going to show you in the next lecture is that the dual solution is fantastic in that it leads us to nonlinear kernel regression methods, which are much more powerful. And we use what's called the kernel trick. So what I'm going to show you first is how to come up with a nonlinear polynomial kernel. And then what you can do is swap out that kernel with Gaussian kernels, hyperbolic tangent kernels, logistic function kernels, and get all kinds of wonderful fits that are much better fits to your data. Okay, so that's for after Christmas. Now I'm not going to go through the actual dual regression solution, because you can see it's. I'll show you quickly. So you got to do a lot, even though it's, as you go through it, you say, well, yeah, this makes sense. This makes sense. It's a fairly complex derivation. So, but the point is, it's a complicated derivation, but all you need to remember at the end is this is the form of the dual solution, and this is the form of the primal solution. And after you've played or written this down a few times, you get the hang of, you're just switching the X transpose from one side to the other. And it shows us they're the same. Okay, so here's some references if you're interested. Chris Bishop wrote a book in 2006 called Pattern Recognition and Machine Learning, which is one of the classics. Very difficult mathematics, but I got the idea of the dual. The dual solution is explained in his book, but it's explained in a fairly complicated way. He does have a very nice introduction using that polynomial fit to a noisy sine wave, though, where I got that idea from. There's the Hastie et al., Tibershani and Friedman book, The Elements of Statistical Learning, which I found I got a lot of really good ideas about regression and all these different methods from. It's sort of the classic. There's another one, again, it's even, I would say it's even more complicated than the Bishop book, called Machine Learning, a Probabilistic Perspective. It's about 1,000 pages long. And then there's two books that I haven't really used today. There's two books on kernels, Sholkoff and Smola, Learning with Kernels, and Shaw, Taylor, and Christiani, Kernel Methods for Pattern Analysis. But the Shaw-Taylor book was the one where I finally saw the light. They had this wonderful derivation of the dual method, starting with the linear regression solution. And that was the first time I really saw crystal clearly why, how it comes about. So, and again, both these actually, I think 4 of those books, the Murph, everyone except the Hastie, in fact, even the Hastie may be available if you Google them as PDFs online. So you don't actually have to buy the books, you can get the PDFs. All right, so that was the talk. Now let's go and have a look at these Matlab examples. Okay, now I did a little bit more work on them, and what you can see is I put everything, I used some if statements, so everything looks the same, but I said, okay, if it's 1, it's a primal solution. If it's 0, it's the dual solution. And so P is the order of the polynomial fit. So let's start with 1. And I also, for the plots, there is probably a way to do this more elegantly, where I actually capture the stuff and print it on the plot, but I couldn't figure. I can figure that out in MATLAB. I couldn't figure it out in Python. So I'm just putting a bunch of if statements, but it gave me practice in writing if statements. Okay, so notice this: n equals 3. Sorry, no, n equals primal equals 1, and so it's the primal solution, and it's a polynomial fit of 1. So let's look at the plots. And okay. And I'm also printing out the values. Notice I've got some print statements in there. So yeah, there's that linear, so I call this the linear primal regression solution, exactly what you saw in my notes. And let's have a look at the primal inverse, 1.33. Okay, you can see you're not quite at 1 and 0.5. You're very close. By the way, I used a pre-whitening of 0.000001, 10 to the minus 6. So now let's switch to primal equals 0, which is the dual solution. And sure enough, you get the same, the fit looks the same. Let's just check the numbers. So there's the primal inverse, 1.33972. Yeah, right down to that last significant digit, it's the same, 972. And same for the regression coefficients, 0.99. It ends with 817, ends with 817 and 0.75. So we're getting exactly the same solution. So let's change to the quadratic fit now. There we go, quadratic dual regression. And we'll do, that was the dual, let's do the primal. And you can see, again, you look, yeah, those numbers look pretty much the same. And then finally, we go to the three, P equals 3 on the, so you can play around with this yourself, convince yourself. Yeah, so there's the, it looks fine, but if I want to change the start, let's go start at minus 2. Look at this, and now you'll see that big, yeah, there we go. Now it swings up. You didn't see that if you cut it off at 0. Okay, now the other thing I should point out is it's fairly easy to modify this. Like, let's say I wanted to say, let's do a 4-point problem. So let's say now I go out to 4, 4 for the x, and let's, I don't know, put a number like 1.5 in for that guy, and let's expand the plot now to end at 5 rather than. Okay, now I'm on, there we go. So now actually I don't need to, probably don't need to go up to -2 there, just start at 0. Now, of course, since I've got 4 points, you get a perfect fit with the cubic. But now if you go to the other one, the quadratic, you're not going to get as good a fit. Yeah, there you go. So the quadratic just gives you kind of average through them. So that's the first one. Now let's go to the other one, which is the sine. So just for curiosity, you see how I actually created this. I created noise using np.random.normal, 0, 1, 10 points. And I created a sine wave, np.sine, did 1 period, added the noise and added 1. And let's see what I've got here. So primal, let's do the primal solution, polynomial fit of 1. See what that does. Okay, so again, I'm just reproducing the figures we got before. If I do a polynomial fit of 3, now you can see that. Okay, now it's funny what kills you sometimes when you're programming. For a while, I didn't have this thing coded in. Let me just show you something interesting. If I here I've hard coded the values, but let's take that out. Let's put a little sharp symbol in there. Let's see, where is that? Yeah, there we go. So, okay, now watch what happens now. Okay. Weird, eh? I can't reproduce. This was driving me crazy. Couldn't reproduce the results. Every time I got a different result using the same. Can anybody think of what's going on here?
I believe you could use a random seed.
Yeah, the random seed. Yeah, if I'd used you're right. This was, each time it's creating a new set of random numbers. That's the point. But you're right. If I'd used set the random seed, it would have have fixed that. But you know, it was driving me nuts. Why am I getting different results every time? Well, it's because it's giving me a different set of random numbers. So so as soon as you take that guy and where is he? Yeah, there we go. Yeah, as soon as you get that back, now we're going to do the same thing. All right. So have fun playing around. One thing you may want to do just for fun is create a couple of higher order, maybe a fourth order fit and a fifth order fit. Maybe I discovered that it gets I tried to go out to 6 or 7 orders and it starts to go a little crazy. So there must be something in the stability issues here. It might be the fact I haven't subtracted the mean or so on. Anyway, getting close to the end, why don't we open it up to some questions if anybody's got some questions. So I'll stop sharing. Oh, we got a bunch of questions in the chat actually. Matt says, Brian can't, oh, sorry, let's start at the top here. How is P related to the number of equations? I think the number of equations is determined by n, the number of points. So P is more related to the size of the matrix. So again, if P, and remember it's P plus 1 if you're including a bias weight. You don't have to put the bias weight in if you don't want to, but it gives a better fit. So P actually, if you think of it as a matrix, n controls the number of rows and P determines the number of columns. So as P plus 1, when P plus 1 is equal to n, you've got as I said, you've got an equal, symmetric matrix, which can be inverted without least squares. But as P gets very small, you've got lots of equations with few fitting parameters, which just gives you not as good a fit. As P gets too large, as P exceeds the number of points, then you're overfitting. So, okay, so undetermined. Matt, is that what your answer there, Matt, was undetermined, right? So, yeah. So, Brian, can you use the kernel trick by using a vector identity? I don't quite understand the question. We'll get to the kernel trick next week. They are vectors, but they're nonlinear functions. So maybe we'll get back to that question in the new year when I do this thing on the kernels, Matt. Can you unmute Matt, Marcelo?
Yes, he's unmuted now.
Okay, I'm just, Brian, there's apparently, I should have said matrix vector identity.
Yeah.
That allow you to replace the X transpose X plus lambda I times the inverse by the other one, XX transpose.
Yes.
And that XX transpose is for the underdetermined case, more parameters than data. Right. So your last case was more parameters than data, 4 parameters than 3 data.
Yes.
Your first case was overdetermined, which is the classic X transpose X solution.
Yes.
So they're apparently, and I haven't quite nailed it yet, but I have cases where you can get the 2 solutions connected by this identity.
Yes.
And then the kernel becomes XX transpose. And so the kernel for the nonlinear basis functions case can be written directly from the vector identities, which then you extrapolate to the generalized case.
Right.
So it's actually quite an interesting result and apparently rests on this identity that I'm still not 100% sure.
I know what you're saying, but what I'm going to show you is that in the kernel approach, you don't actually write it as X transpose. You write it as K of brackets X, Xi, Xj. So for example, I'm going to show you, just to give you a heads up on where I'm going with this, that the kernel for this, kernel for polynomial regression is 1 plus, brackets, 1 plus xi xj raised to the power p, which is wonderful because you never have to, all you have to do is change the number, change the value p, and you make, and it creates its own current, it creates a matrix. So yes, it is a matrix, but you're not creating it by multiplying x transpose x. You're creating it by a set of values. Now, when you get to things like, that's fairly linear, but when you get, or it's nonlinear because of the power p, but when you get to something like the radial basis function, which is you can also have xi minus xj or xi minus xj squared, which leads you to a Gaussian solution. And that Gaussian solution leads you to what's called the radial basis function. And then you can also do the logistic function or the tanh function, which is the cornerstone of the feed-forward network. So I'm going to do all of those in the next lecture. We're going to look at all the different nonlinear fits. So, okay.
Do you have a good reference for the dual? Because I couldn't find it. I was trying to find something.
I'll send you this. The one I liked the best was that Christiani. It's fairly mathematical, but they have a wonderful example in their introduction. Let's see. Let me just get the PowerPoint back up. Yeah, this one here, Shaw, Taylor, and Christiani, kernel methods for pattern analysis. If you Google that, you'll actually be able to download it. But I'll email you if you want to send me. I probably got your email address, but why don't you?
I'll send you mine.
Yeah, I'm officially. I'm no longer. You can get me at brian.russell@cgg.com, but we're no longer part of CGG. We're now supposed to put brian.russell-contractor@cgg.com, and eventually it's going to be changed to geosoftware.com, but that's going to be a while. So
which one do you want me?
Just do the easy one, brian.russell@cgg.com. I think that'll get to me. It's still, okay. It'll still get to me.
Hey, Matt, I have an example that you will like because you work in this. I learned a bit of radon transform from you at UBC. So you see in the radon transform, we used to use the dual. And you can think from a physical point of view, what it is you suppose when you do the least squares radon, right? That's a very generic example because you can think of the same for any transformation. So when you do the primal, is like you first do a mapping to the model space and then you deconvolve the operator. So in the case of radon, the operator is divided by the frequency. So when you do the dual, what you do is you first you first deconvolve the operator from the data, and then you map it to the model space. That may trigger some memories from you.
Yeah, I think I read a little bit that in one case you're doing AX, and think of it in the context of ridge regression, that you're minimizing the L2 error of AX equals B, subject, where AX equals B and X is the parameter space, the slope and intercept, subject to plus a small number times the parameter vector squared, right? That gives you ridge regression.
Right.
So you can think of it minimizing the difference between AX and B in L2 with a constraint that the parameter vector norm is less than some constant, positive constant.
Is that to get the dual solution? Or
no, the dual's the opposite.
You do it the opposite way, okay.
Yeah, you do it the opposite way. So in one case, your constraint is what you're minimizing, and the role of constraint and minimization switch.
Yeah,
okay.
Exactly, yeah.
And that's, I think, Daniel, that's just what you said.
Yes, exactly. That's what I am saying.
Yeah,
It's just that I'm giving you the example in the case of the radon transform because it's a signal processing example, whether you decompose first.
Let me turn off my background here.
Yeah, you decompose first in the data, then you map, or you map and then decompose. So that's very much the thing.
If you have this book, Inverse Problem Theory, the latest Tarantola, or the last one Tarantola published, it's on page, and this is the first time I think he has a derivation in one of his appendices. Yeah, page 66. Now his solution is a lot more complex because he puts in data covariances and model covariances as well, because he's showing how to do basically a full inversion that'll give you the stochastic solution. But he definitely has the dual, and he doesn't call it. He just says, let me first give you the solution, and the posterior Gaussian is given by any of the three equivalent expressions. So he actually has three equivalent expressions in there. So Daniel and I were talking about maybe there's a way to modify that to come up with the nonlinear kernels. I haven't seen anybody do that, but.
Yeah, don't forget that you're still talking linear. If you're doing, if you're linear in the model parameters, and they're multiplying the basis functions or the elements of polynomials x squared and so on, it's the same form. It has to be, because it's linear in the model space, if you like. It's linear in W naught W1, regardless of what goes after them.
So you're saying it might not make sense to do it nonlinear because our models are linear.
Well, this only works if you're linear in the parameters that you're trying to find.
Okay.
So if I had W naught squared in there, that wouldn't work.
Okay.
That's
I see what you're saying. Yeah.
So when you say nonlinear, you're saying nonlinear in the bases.
But not nonlinear in the weights. The weights would still be linear.
Yeah. That's the point. And so that's why you can do this for the kernel trick for the linear case with nonlinear basis functions. That's how I understand it.
Yeah. No, you're right. You're right. So it's the basis functions that are nonlinear. Yeah.
Right. In this case, polynomials x squared and x cubed. But I like what you've done. And what I've been looking at is the geometrical interpretation of x transpose x. And you're in the column space. So what's really nice is x transpose x, when you said in the first slide, you take the inverse. Well, it only works if x transpose x does not have zero determinant, which means that the columns of x are not linearly dependent, which means that your rank is equal to the column rank of x.
Yeah, the best guy. Sorry, go ahead.
And finally, the point is you can represent this all geometrically. I found a beautiful geometrical representation, and it turns out to be very important to put the ones in the design matrix, as it's called, and not leave them out, because it has a very nice geometrical significance.
So you're saying the ones from the weight, the bias weight.
Yeah, why not leave it in? I mean, you could always start your x's at x0, x1, x2 up to xp, and fix x0 to be 1.
Sure.
So if you want to do an inner product, do it that way. And what that's really saying, this is an old thing of Felix Klein and geometry, is that you then have a data element that's the dual to the model element. So you have a vector W0 to WP and X0 to XP. That's a dot product. And that's a plane that has one more dimension. Yeah. So that the dual space is the set of linear forms, i.e. inner products on elements of the vector space when you just have a linear multidimensional space, x0, x1, no squares or anything.
Interesting, yeah. Well, you know, the guy who does that best is Gilbert Strang, right? And he's got a new book. Well, it's not that new now. He actually, if here's another recommendation, if anybody's interested.
Oh yeah, I got the book.
Learning linear algebra and learning from data. He actually shows how all of machine learning is based on linear algebra. So.
Yeah, I'm finding that the interesting thing about this, Strang is probably one of the few, but even he is a little light on the geometrical pictures of all this stuff. And that's really missing. You get a huge insight when you see some of these pictures. And I'm currently writing this up in the book that I've started on, exactly this stuff. So that's why I was very curious to see what you're going to present.
Thanks. I mean, to me, this is so outstanding because, or so amazing that I've discovered this by looking at some of these books, that when we first wrote Emerge and I did my PhD thesis, I thought of all these methods as quite unrelated. I saw the, multilinear regression as one set of techniques and radial basis functions and generalized regression neural networks as a completely different set. And now I realize this underlying connection between them is based on this kernel or this dual representation, and it just blew my mind when I saw that. It's wonderful.
Yeah, I think machine learning or when you're looking to drive towards deep learning and neural networks, you have to start with a good understanding of linear regression and simple linear regression, the two element case that you presented initially, because you get the geometry feel and then you can translate that to the linear algebra feel.
Yeah.
And one of the things that's a big deficit in classical teaching matrix in math courses is they do matrix multiplication as a bunch of inner products.
Yeah.
But the better way to do it is to use the outer product summation of column vectors.
Yeah.
Because that gives you an insight into the rank of the matrix and the null space.
Yeah. And I think Gilbert Strang does a nice job of that in his actual book on linear algebra, because he starts with his geometric picture and shows how you got lines intersecting like this is the equivalent of doing your matrix multiplication. So
yeah, and there's a great YouTube video in 3 Blue 1 Brown where they talk about the overdetermined and underdetermined cases.
Wow.
And what it means to go project. See, if you think about it, if I take a matrix that has 2 elements in it and I project it to 3, I can do anything I want. I have 1 degree of freedom to get into that 3rd dimension. Whereas it's different when you go the other way, because you can do the straight projection of 3 into 2, but 2 into 3 puts you in the wild blue yonder. Yeah, that's why you have you have ax3 equals 0 because it's still sitting in the 2D space, so you can't see it.
By the way, Matt, I want to interrupt you, but I better make sure I've answered all of the questions.
Okay.
Anybody says, hi, Marcelo, a side question. I think you mentioned before Cruz offers some trainings. Oh yeah, so that's so that came from, so Marcelo, you answered that. That's good.
Yeah.
Okay, we're getting close. Well, we're not close. We're over. We're 10 minutes over. But if anybody who's still on the line has any questions, I know it's been kind of the Matt and Brian hour for the last little while.
Well, I can just finish the session. And then if you have more conversation, you can do these without the recording.
Right. Okay. Because the recording is still going on. Okay. And anybody wants to stay around, I'm okay for a little while.
Okay. So I'd like just to finish the session. So this is the last lab in this year. So I'd like to wish everybody happy holidays. And don't forget to follow us on YouTube, LinkedIn, and Twitter. so you can stay on tune with everything. So thank everybody and see you soon.
Great. And you can, I'll give you that PowerPoint, Marcelo. So anybody who wants it, you can send it to them. Okay. Oh, you got it already.
No, I got it already. So we
there was one typo. I better send you the updated one.
Okay, just that 6 to 9. Okay.
Okay. Thanks, everyone.
You guys have a great Christmas.
Yeah. Thanks, Matt, for having.
Okay. Bye.
Bye, everybody.